Thank you very much. So, a couple of weeks ago, I was having a chat with one of my colleagues by the coffee machine, and we were talking about this presentation I was going to give today. And my colleague had some thoughts about the topics I'll be having here that I recognize from quite a few people I've met over the time. I'll be talking mostly about tuples and pattern matching. And his reaction when I said I was going to talk about tuples was that that's really just syntactic sugar. What's the big deal? And hopefully, after this presentation, you will agree that there's more to it than just syntactic sugar. So, I'll be talking about functional patterns for the object-oriented, and my background for this is that I have a background in Haskell, using Haskell as a functional language, and at Click, where I'm working now, I use mostly C#. And I've seen that there's a lot of things that you can leverage that I learned from working with Haskell in C# that older language like C++ and such is harder. I gave a presentation about link and lambda expressions a number of years ago, which is also on the same topic. But today I will talk about tuples and pattern matching, and in particular I will show you how those constructs are used in a functional language like Haskell. So there'll be a lot of Haskell code in this presentation. I don't know, any of you know Haskell here? Yeah, some of you? Okay. I don't assume that you'll have a lot of Haskell knowledge, so I'll explain the Haskell that I'll show. But if there's any questions, of course, you should raise your hand so you can follow my examples. So, first thing I'm going to do hopefully what will be a little repetition about what tuples and pattern matching are. Everybody here know what a tuple is? Yes? Yeah? A tuple is basically an anonymous data type. Sort of a struct that you can build up by just combining values without giving it a name. A small example would be something like this. So this is a standard function you would find in C# coming from the maths library. So it's a function that takes two integers and divides them, returns the integer part and the remainder part. This has been part of C# since the beginning, at which point there were no tuples at all. So for a function like this that actually returns two values, you would have to return one value, and the other value you would have to provide as an output parameter. That's one option, or you could build a struct around this and package it like this. But for a low-level function like this, you would typically do something like this. In C# you have quite a while been able to use a library structure called a tuple. And with that you could find a signature like this instead. So instead of returning an int and having an output value, you would return a tuple containing two ints. But starting off C# 7, which was released about 2 years ago now, you can write this instead. So tuple has become native to the language, which means that instead of using a class like this, you would just wrap them in parentheses and you would get the structure you want. So, a little example how you can implement this. If I want to write a little wrapper function for the original div_rem that uses tuples, I could write something like this. I would call my function, the div_rem, assign the quotient and reminder in the old style, and then when I return the value, I just build a tuple as well, like this. So I just wrap those in parentheses, and I get this type. So far, it is pretty much just syntactic sugar. It's a convenient way of writing something that was a little harder before, but the interesting thing comes when you want to actually access these values. Because now, in C# 7, you could, let's say we want to write a function like this, where we want to take a value like this and print the result in a nice form. So 13 divided by 5 would be 2 wholes and 3/5. What we can do now with the new method of using tuples is that we can write like this. So we can call our div_rem function, returns a tuple, and then directly deconstruct that tuple here. We can just assign it directly like this. And as we before, when we were using the tuple library, we had to access those individual elements as item 1 and item 2. Now we can just access those values immediately, named here. And now if we want to write them, we can just print them out in whatever form we want. So this is a little more than just syntactic sugar compared to what before, and I will show you how this combines with pattern matching to give you something that is really nice. So over to pattern matching then. Does everybody here know what pattern matching is? A couple of you? This is a little harder to explain, and it's probably because it's very rarely used in an object-oriented language. But C# introduces a function for this as well, and I will just give an example of how it works. You want to find a seat? Yeah. So let's say you want to define a function called compute area that takes as argument some object representing some form of shape. And we want to have this function, depending on what shape it is, you want it to compute the area of that shape. So in this case, we will do different things depending on what type of shape it is. So if the shape is a square, well, then we have to typecast that object to a square. And once we have done that, then we can actually access the side information of that square and compute its area. If it's on a circle, on the other hand, then we need to typecast it as a circle. And once we have done that, then we can access the radius here. Of course, a square doesn't have a radius, but a circle certainly does. And then we can return the right value. And so on for rectangles and whatever shape it is. Now with C#, there are some benefits of using pattern matching for this instead, because this becomes a pretty nasty series of if-then-else clauses and typecasting. But with C#7, we can write like this instead. We can do a switch directly on the shape, and then each case will be one type that shape has. So previously we could do a switch on enumerables, but with C#7 we could do that on objects like this and pattern match on the type. So if it's a square, that's one of the cases. We immediately have a handle for a square object, so we can return the area of that square. If it's a circle, on the other hand, we can just add the compute the area like this. And if it's a rectangle, and so on. So it's a very nice way of doing this type of pattern matching when you want to do a function that observes a data type, and it's not just a part of a data type, but something that observes it from the outside. Of course, you could argue that shouldn't area be an operator or a function or method of the shape itself. And yes, sometimes it could, but sometimes that is harder because this object here might be coming from some third-party library that you don't have access to. And at that level, you can't add a member function to it. You have to do something that observes it from the outside. All right, so that's a very quick introduction to, or a repetition hopefully, of these two features. Any questions so far? No? So, I will spend the rest of this talk talking about an application of this in the domain of code generation and API testing. And for one reason or another, I've ended up in a lot of projects over the years where code generation has been an important part of the job I'm doing. And when I joined Qlik, my first job was to participate in a group that was developing an SDK for doing API interaction with our tool, QuickCheck, through .NET. And to do that, we would have a specification of the API that the tool provided. In our case, it was a JSON RPC protocol over WebSockets, for those of you who know that. But basically, what we had to do was we would take the API objects and generate JSON that would represent these function calls to the system, and then parse responses coming back. And we would get specification that would look like this. So this is a method that can be used to the API to create an object. It's a generic object. I'm not going to talk much about what that means in our scenario, but it's some form of object that provides methods for you. And this method takes two arguments. It takes a set of properties that defines the object, and it takes this argument and it returns the created object itself and some other output parameter like this. So we would take these functions and the definitions of these data types, and we create a lot of C# code that will allow you to interact with these method calls that were actually unstructured JSON, and we will allow you to build C# structures that would encapsulate the types of those. It's a very convenient way to get some type safety layer on top of JSON that is very unstructured otherwise. So one of the methods we would create for this, or generate for this, would look like this. So here we have our asynchronous version of the create object that you could call from C#. And you can see the name here comes from the name here. This is the string you would actually emit in the JSON call. We will have the incoming parameter here. This is a class that would have been generated based on the type information of this class, and so on. And what you're seeing here is a low-level hand-coded call to a send async that will actually take a request object, which in turn will be packaged into JSON and turned into a JSON string. And there's a lot of layers to this in terms of what we generated. So this is sort of the lowest level of those layers. And when you want to do code generation, the sort of first gut feeling is that it's all about concatenating strings. And at some level it is. But has any of you done any code generation? Yeah, a couple of you? Yeah? So you'll find that if you want to produce something that is a little more complex than just basic calls, you very easily run into problems if you just try to concatenate strings, where you get like mismatching parentheses or missing white spaces in the wrong place or stuff like that, or just typos in the names. It can become very, very tricky to debug, and it's very time consuming. So what we did when we built this generator for this API was that we used a library from Microsoft called Codom. I sort of assume that nobody here has used that if you haven't used code generation. Oh, you have? Okay, one has used Codom, good. So Codom is basically a library containing a number of classes, and those classes represent different type of program structures. So if we want to create an expression that would encapsulate this expression, so x plus 1 minus 1, then we would define that through a series of class instantiations like this. So we have constructor functions. We have an outer binary operator representing the plus. So code binary operator expression it takes 3 arguments. It takes the left and the right expression and the operator type. These also come from the library. And the left expression will be the variable x. So we have a code variable reference expression. And the right expression is another binary operator, which again is nested like this. And here we have the primitive expressions 1 and 1. So what's the purpose of this then? Well, one of the interesting things about an expression like this and a structure we get here is that it's totally language independent. This expression is an expression you could probably use in almost any programming language there is. It could be C#, it could be Java, it could be Haskell even, Python, whatever. Almost every language has structures for doing this. But the syntax differs a little. For x plus 1 minus 1 might not be a big difference, but if you use something like a not operation, for instance, it might look different. And what we get when we do this is that we actually build up this type of tree, a tree that represents the structure of the program. It says nothing about what that program does or what it looks like. It just gives us a representation of its structure. This is called an abstract syntax tree, for those of you who are familiar with that term. And why do we want to do this then? Well, because at this point we have a structure that represents the logic that we want to somehow manipulate. And now we can start defining functions on this structure. We have the structure here, but we want to print it as, in our case, we want to print it as C#. So you want to have some sort of operation that allows us to print C# from this structure. And now we really have 2 options. We could either go the object-oriented way, and the object-oriented way would be to give the responsibility of doing these operations to the individual nodes. So we could say that, okay, we have a binary operator node that should have some sort of override of a virtual function that says print, for instance, if we wanted to print itself. ToString is what you use in C#. And so the individual node could know how to print itself by knowing that if it's a binary operator, I have to print the left one, I have to print the right one, and I have to combine them with the operator. But the problem with that is that when Microsoft developed this library, they did not know what you want to actually write from this. They couldn't guarantee that you actually want to write C# or Java or whatever. I could want to generate Haskell with this. So having those operations as member functions in the nodes would not really be a good approach, because then we will run into this problem that I want to do something with this structure that is totally valid, that is not represented within the object itself. So instead we could go the functional way, which is what Codom does. It allows you to, instead of having those operations be the responsibility of the nodes, they expect us to write functions that traverses this tree, so that one function will be responsible for doing the whole operation for the whole tree. So that means that I can write a function that takes a tree like this, a codom structure, and traverses all those nodes and prints Haskell from it. All right. So now I'm going to turn to Haskell and show you how this is done there. Because defining this type of abstract syntax trees and functions on them is very, very convenient to do in Haskell. And if I want to have a data structure that represents a tree like this, that we saw in codom earlier, I could do something like this in Haskell. So here we have a declaration of two types. We have the operator type, which is basically just an enumerable, where I have 4 different operators in this case: add, sub, mul, and div. This is not too tricky. But the other one here is more interesting. This is a data type which is called algebraic data type, sort of fancy name, but it's a type that comes in 3 different flavors. An expression can have 3 different flavors. One is the number flavor. It could be a number or a leaf node, in which case we have int as an argument. So a number node contains an int. It could be a variable. A variable node will contain a string. Or it can be a binary operator. And a binary operator will, of course, have an operator, and it will have 2 expressions. So it's a recursive data type. And now that we have defined a data type like this, we can construct our tree like this. These constructors here are turned into functions in Haskell that are used to construct these data types. So here I have first the top binary operator. It's going to be an add that matches this one. Left expression is a variable x. Right expression is a binary operator with a subtract and the 2 numbers. So now we have this abstract data structure, just like we could create in codom. And now we want to do some operations on it. And the first operation we are going to write on this data structure is the operation that prints it. So we want to write a function, print expression, takes an expression as an argument, and returns a string representation of that same expression. And this is where we start pattern matching. Because this expression comes in 3 different flavors. So writing a function that prints an expression will be basically a function that does 3 different things, depending on what flavor it is. So if it's a number, then we immediately have access to that number handle. And then we print it as a string. Show is a function in Haskell that takes a value and prints it as a string. If it's a variable, well, then we already have a string. It's an ID, so we can just return that immediately. And if it's a binary operator, well, then we have to print the 2 left and right expression. This is a recursive call up here. And we have to print the operator, and we have to add parentheses around it. And then this builds a list of strings. And concat just takes a list of lists and concatenates them into one. So this gives us one big string from it. So that's how you would do that in Haskell. Any questions so far? Okay with the Haskell syntax? Yeah? If you miss the union type? Or if you miss one of them, you mean? Well, there are flags for controlling that, so you'll usually give warnings. You can turn them into errors if you want. Yeah. All right. So let's write one more function, a little more interesting one this time. So we can see that this tree here obviously has some room for simplification. We have a node here that is 1 minus 1. We know we can turn that into a 0. So let's write a function that takes one of these trees and tries to simplify it as much as possible. So it takes an expression as an argument and returns a possibly simplified expression. So again, we pattern match on the expression. If it's a number or a variable, then we are at the leaf node, so we can't do much. We just have to return the expression immediately. The underscore here is a don't care. It means that I don't know what's in there. I just return the original expression. But if it's a binary operator, then we have a more interesting case. Because what should we do here? Any suggestions? Yes, exactly. We need to simplify each of them. We need to simplify the subtrees. And after we have simplified the subtrees, what should we do then? Go on simplifying, yes? If we simplify the subtrees, then if those both simplified subtrees are numbers, then we could actually simplify them based on the operator. And this is where the concept of pattern matching in tuples comes in handy, because in Haskell we can now do like this. We can create this tuple representing the two simplified expressions immediately like this. So here we do a switch statement on a tuple where we have the simplified left expression and the simplified right expression. And if they are both numbers, we can pattern match on whether they are numbers inside the tuple. Well, then we have the case where we can actually simplify stuff. So now we can return a number, and here we would actually do the evaluation. So this is a function we need to define as well, that's based on this operator. So if it's a minus, we have to do subtract, and so on. So here we just create that and turn that number into this expression again. And if they are not both numbers, so in the other case, well, then we can't do much more simplification, but we want to keep those potentially simplified sub-expressions. So then we just create a new binary operator with the original operator and return the two new simplified expressions like this. It's pretty nice, I think. It's a very convenient way of doing stuff like this. Of course, we could simplify it more if we were a little eager, and you can have that as a home exercise if you like. For instance, if you do add with a 0, then you can return the other expression and so on, right? But I'll stop like this for this presentation. All right, so that's some on pattern matching and tuples in Haskell. Now I'm going to switch gears a little. I'm going to talk about a library in Haskell called QuickCheck, which I find very, very interesting, and I'll show you some techniques for using this to do some testing exercises in Haskell. So QuickCheck is a library that provides functionality that allows you to generate random test cases. And the goal is to just generate tons of test cases and see if your program works based on those test cases. I'll show you how this works and the mechanisms around it. And what QuickCheck does, it adds a type class called arbitrary. A type class in Haskell is nothing like a class in object-oriented languages. This is more similar to an interface. But basically what this says is that there is some sort of type class here that any type that wants to be a member of this class needs to implement the functions that are defined here. So if I want to make my expression type a member of this arbitrary class, then I have to implement this arbitrary function for the class. And the arbitrary function has this type, gen A, which is gen also is a type coming from the QuickCheck library. But it's basically a function that tells you how to generate a random instance of that value. Gen is a monad, if anyone knows what that is. That's not really necessary for this talk, but it's encapsulates some logic in Haskell. So we're going to make our expression class an instance of the arbitrary type. The way we do that is like this. So instance arbitrary expr. Expr is our type, where and now we have to implement the arbitrary function for the expr type. And as you remember, expr comes in 3 different flavors. So we want to randomly generate one of those flavors. So basically we're going to write 3 different generators, one for each of the flavor, and then we're going to let QuickCheck randomly choose one of them to generate. So there's a predefined function called oneof in QuickCheck that does exactly that. It takes a list of generators and randomly picks one of them and executes them. So the first generator we're going to write is the generator that returns the number flavor, and that will look like this. So first we generate an arbitrary integer. Then we take that integer and wraps it in the num construct, and there we have an expression representing the num flavor. Now there's some interesting things to say about this code. And the first of all, you can see we never actually say anywhere that it's going to generate an int. That information is not there, at least not visibly there. But this is an interesting thing about Haskell, that Haskell has a very nifty, advanced type inference mechanism that makes it so that if a value has to have one specific value, well, then it has to have that value. And Haskell can use that to force stuff around the language, around the program. So in this case, num here is a constructor that takes an int as an argument. That means that n here has to be an int. That means that n has to be an int there. That means that this arbitrary function has to be the function that generates an int. So this has to be the arbitrary function coming from the int instance of the arbitrary class. And of course, int is a built-in value, built-in type in Haskell. So the QuickCheck library provides function for generating an int. That way we can generate random number flavors. Then we want to do the similar for the other flavors as well. So for elements, I will just do like this. Or for variables, I will just do like this. So I will just let it pick one of these 3 random names. I don't really care. In a real world generator, you probably want to do something more advanced there, but this is sufficient for demo purposes. So I just let the QuickCheck pick one of these 3, and then I wrap that identifier in the variable construct. Then we have the binary operator again. This is a little more interesting. This is usually the interesting case here. So what should we do here? What should we generate for the binary operator flavor? Anyone want to take a stab at it? Yes, we'll have to do a recursive call, to arbitrary. And first of all, we want to generate the operator. So you want to have a random operator, one of those 4 operators we had. Then we want to have a random left expression. Then we want to have a random right expression. And finally, we take those 3 values and just wrap them with the binary operator. And again, this is pretty nice code. You just say arbitrary, arbitrary, arbitrary. And these types here and the functions that I call are forced upon it based on the values we have here. Binary operator takes an takes an operator and 2 expressions. That means that up here must be an operator. That means that this must be the arbitrary function that generates an operator. This has to be an expression. That means that this has to be the one that generates an expression, and so on. But now, QuickCheck provides these type of generators for almost all the built-in types in Haskell, even for functions actually, which is really interesting. But that means that QuickCheck also has predefined function for generating tuples. So I can do a call to QuickCheck that generates for me a random tuple. So I could turn this code into this. It is, isn't it? So how does this work? Well, this is a tuple with 3 values. And QuickCheck has a predefined arbitrary function for generating tuples of 3 values. So Haskell will know that this must be the arbitrary function that generates a 3 tuple. And since these values have a type forced by the binary operator, this has to be the function that generates a tuple with an operator and 2 expressions. It's very nice. Yes? It's a function. It's a function, yes. It's a function that has to be the function is member of this class, but the exact function call that is called is forced by the value it generates. So we have a lot of these overloaded functions actually, that all come from the same, that belong to the same class. We'll have some restrictions on the type signature. They have to be of this type, generator, A. All right. Yes? Be the same as? Yeah? Semantically, it's the same thing, yes. But this is one of the advantages I feel of having this as a native part of the language, not just as a library. Because the fact that these are native to the language makes it natural to include functions on this for libraries like QuickCheck. And tuples have a lot of other advantages as well over, for instance, just using a struct, which you could otherwise be doing, would be fine. But once you use a tuple, you get all these functions upon them. You, for instance, are able to compare them easily. You don't have to write a compare function. You can they can be ordered. You can print them in a nice way. There's a lot of extra functions on top of tuples that you get for free when you use the tuples that you don't get if you just use a struct. And in Haskell, you have libraries working on this. So you, for instance, have convenient way of generating tuples like this. But yes, semantically, it's exactly the same as just doing it 3 times. It's just more convenient. I don't have to define this anywhere. This is defined in Haskell, in the QuickCheck library. This comes from that library. Yeah. All right. So now we have a function for generating a random expression, and also we want to make the operator an instance of the arbitrary class. And that will just pick one of those 4s, like this. So this is all the code required to generate a random expression of this, yeah, rather limited language, of course, but still, it's very nice code, I think. So now we have a way of generating a random expression, but of course, what we want to do is to run some tests with this. Random expressions in themselves aren't very interesting. We want to have something to actually use them for. And one of the problems with random testing is that, well, you get random cases. You don't really know, like when you're writing unit tests or directed tests, you know what the expected results is. That you can't do directly for random cases because you just don't know what the cases would be. So what you have to do is you have to come up with some properties of your data type or what you want to test that you know must always be true. So here we would apply property-based testing. And the idea would be that we want to find some sort of behavior that we know should be true whatever test case we generate. Because once we have that, then we can just generate tons of test cases and see if that property holds for all of them. And if it doesn't, then we have found a bug. So what kind of properties could we write for our expression data type? Anyone have any thoughts? No? So I'm going to write a property that says something about the size of the tree when we do simplification. So I'm going to write a property that states that if I do simplification of expression, then the size of the result of that simplification must always be smaller than or equal to the original tree. And by size, I just mean the number of nodes in the tree. So first, we're going to write a little function that computes the size of the tree. So this will be another exercise for you. Should be pretty straightforward. Now you know everything about pattern matching. The size takes an expression and returns the number of nodes. So we do, again, pattern matching on the flavors. If it's a number or a variable, then we just return 1. That's 1 node. If it's a binary operator, then we do what? What's the size of such a tree? Nobody? It's not that hard. Exactly. Sum of the size of the subtrees plus 1 for the current node itself. So it's just 1 plus the size of the left tree plus the size of the right tree. That's it. Now we have this function for computing the size. Now we want to write a property. And a property in this case is a predicate. And this is typically how you would write, this is sort of a naming convention for properties in Haskell. So prop simplification reduces size, I call it. It takes an expression as an argument and returns a Boolean value. So I can take this property, I can send an expression to it, and if it is true that the size of the reduced expression is smaller than or equal to the original one, then it's okay. If it's not, then I get false here and I have found a failure. So, definition of this is pretty straightforward. We take an expression as an argument, and then we just compare the size like this. So the size of the original expression should be greater than or equal to the size of the simplified version of that same expression. And now that you have this property, And we have a generator that states how to generate random values of this. We can combine them. So we can write a loop that just generates an expression, applies this function, and if it's true, that's okay. If it's false, then we have a bug. We have a counterexample to our original expression. If we don't have a counterexample, then we can generate one more, and one more, and one more, and we can generate thousands and hundreds of thousands of these, and see if we can find anything. So let's go, do that. So here I have a little program that does that. So this is actually going to do, no, you don't see it. I have to move it over here. Let's see. All right. This is actually going to do a random generation under the hood, so it's always a little scary because I don't really know what I'm going to end up with. But we'll run it here now. Boom! We have a failure. That is a real bug in the code we just wrote. And you can all see what the problem is, right? So that's the other problem with random cases, that they turn out to be very, very confusing. They contain a lot of noise, which makes them very hard to debug. But this is where QuickCheck is really, really interesting, and where I usually get excited. I'll show you here. Let's see. Because QuickCheck not only provides the arbitrary class, arbitrary function. This arbitrary class also provides another function called shrink. And the purpose of shrink is to take a value of this type and produce a list of smaller versions of that same value. And the idea would be that if you have this function, and we have an expression that we see does not fulfill this property, then we can create this list of shrunk examples, smaller examples, and then we can apply the property to each one of them in turn. And if we find a case that fails, that means we have found a smaller counterexample. And once we have done that, then we can do the same thing again. So we can take that smaller example, shrink it, and try to find a even smaller than that. And we can do that again and again and again until we end up in a case that we can't shrink anymore. That will be a minimal counterexample that shows you exactly what needs to fail for the property to fail. Now there's no guarantee that what you get when you shrink, that the bug you actually found is the same as the original one, but that doesn't really matter. What you're looking for is one failure. And if there are multiple failures here and you sort of skip between them while you're shrinking, well, then you fix the first one and you can run again and you can find the next one. So let's define this shrink function for the expression. How would you do that? Well, we have our arbitrary instance, so the arbitrary function we already defined. I'll print that. Then we want to write the shrink function. Shrink takes, in our case, an expression as an argument, and we want to do pattern matching, of course. What we do with this value depends on what flavor of the expression it is. So if it's a number, then we shrink the inner number. Ints are again predefined as part of QuickCheck, so we could use the shrink function from QuickCheck here, which takes an int and shrinks it. This gives us a list of smaller versions of that integer using some smart way of doing that. So if you have a million, you don't get a list of a million values. You would do some sort of binary search on that value to find something smaller. And then this gives us a list of integers. So then we just do map num. This applies num to every element of that list. So this means that we just get the list of number flavors depending on those shrunk values. If it's a variable, well, depending on your implementation, you would do different things here. But I just said in this case that variables can't be shrunk. So I will just return the empty list. There's no way to shrink a variable. And then we come to the binary operator. Again, this is the interesting one. Because what do we want to do here? How can we shrink a binary operator? We could compute the expression, simplify it. That would actually change the structure of the value. So that would not be what I would recommend in that case. Exactly, we can try each of them. We can just discard the whole binary operator itself. Just return one of the sub-expressions. So those are two possible ways to shrink it. We can just take one of these sub-expressions. This is a list now containing two elements. Just the left expression, just the right expression. And we will try them in turn when as part of the shrink operation. But we can also do more here. If this is not okay to do, or if none of these still fail after doing the shrink, we can also shrink the inner values here. So we can shrink the operator. This is a shrink function applied to the operator. This is a lambda expression in Haskell. The tick here is just some idiomatic Haskell. It's a different version of what you're seeing here, but it's just a different name. So I will apply this one to the different shrunk operators. And for each one of those, I will have a new binary operator with a shrunk version of the operator, and I'll keep the two left and right expressions. And I can do the same thing for the different sub-expressions. So I can shrink the left expression, and I can shrink the right expression. And this gives me a long list of different potential shrunk expression that I can try and see if I can find something smaller. But again, yeah? Well, there's some things that you really need to keep in mind when you do this, and that is that these values are always smaller than the original one. If they're not, if you somehow produce the same value over and again, then you will just go into an infinite loop. That would not be good. But you said it. The fact that the potential numbers here is big is not that big a problem in Haskell, because everything is computed lazily in Haskell. So you never actually compute all of this. You just compute the one you actually try. But that's a different part of Haskell that I'm not going to talk about here. Yeah. So it's for those of you who are familiar, how many are C# developers? Yeah, so you know about yield return and that type, right? This would be more like doing this in a yield return. You just compute them on the fly as you are generating those different random values. So you don't actually produce this all at once, unless you actually are at the point where you can't shrink it anything. You're already at the minimum. Then you have to go through all of them. Anyway, back to this code. So now we have written this function, but again, Tuples is a part of Haskell. It's a native part, and QuickCheck has predefined function for tuples. So you can also use the function for shrinking tuples. So I don't have to write these as 3 different operations. I can just write like this again. I can just package these 3 values in a tuple, call the shrink function that shrinks a 3 tuple, and then I can just build my expression like this. Yes? Yes, I talked about that as part of this. So shrink is a function that you define for your instances of the arbitrary type that takes a value and produces smaller versions of that same value. That's up for you to define, but I would, I think in this case I would just say that would go, so you have add sub mul div, and the one to the left in the list is smaller than the other one. But that would be up to your implementation to choose that. It might be that you actually don't want to shrink operators at all, that there's no shrink. All right, so now we have this function. Now we can start shrinking that original case we had. So we had this one. And each time I press return now, I'm going to run the shrink operation once. There we have a smaller case. So what did it do? It removed the outer y minus, disappeared. Next step, what did it do now? It removed this part, and so on. And now I think you can see what the problem is, right? We can't shrink it anymore. Yes. Infinite, right? This is a divide by 0 operation. We didn't take care of the case where we were doing divide by 0 in the simplification of the expression. And these cases are very, very, very valuable. It's real nice when you're using QuickCheck and you end up with these small cases, but they are so focused on exactly what is required to trigger the failure. And I'm going to talk about one of the cases where I actually used this, unfortunately not at Click, but at a previous company, where we used this for API testing using a product we call a script generator. So I wrote a program. Right at that point, we were selling a tool that had a script interface. So we could write scripts for controlling what the program would do. And what we would do is we would write this program that would just generate a random script, big random scripts, and then we'll run it through the tool. And what would the property be? those can be very, very complex in this case, but I took the shortcut, and I just want to look for crashes and null pointer exceptions. Because I knew that whatever script I was to give to the tool, it should never crash. And we found hundreds of bugs. Most of them, and almost all of the cases that we ended up with, I started up by generating scripts that were 500 rows long, pretty complex expressions doing all kinds of strange things. And the test cases we ended up with was almost always 2 or 3 lines of code long, which was really cool. And I spent way too many hours just looking at this shrinking because it was so nice. You started up with a 500 row script, and you will see that it will try to remove the first half. And oh, I'm up left with this. And you will see it sort of narrow down onto functionality that will actually trigger the bug. It was really, really cool. We also found some very esoteric bugs, like there was one bug that was actually 32 lines long. And the reason was that we had this functionality in the tool that you could flip on and off. And apparently there was a case where if you flipped it on and off quickly 32 times within less than a second, then I don't think a user would actually trigger that one, but I thought it was funny. If you did that, then there was a buffer overflow and the tool would hang. Yeah, so that was an odd one. I laughed at it, but I was looking at it doing the shrink. I was like, "What the hell is it doing?" It's just all these different lines ending up, and it was narrowing down to all these structures. So very nice. I love that technique, and it's very interesting, and it was extremely valuable in that case. And I think we use this type of randomized testing way too little in the object-oriented world. I have seen very few people talk about this in an object-oriented environment. In Haskell and functional languages, this is used a lot. And if you go to a company such as Ericsson or Klarna, this will be a type of testing technique that they use quite a lot. There's a very nice video from John Hughes. He's one of the inventors of QuickCheck, where he talks about some applications he did on testing a database for race conditions using QuickCheck. I think that was in what's it called? Language that they use at Erlang. But still, same type of technique. This is very entertaining, very nice talk. I can highly recommend it for those of you who have time and want to dig deeper. And another environment where randomized test generation is used all the time, that's in hardware verification. If you develop a microchip, like when Ericsson developed their 5G base station chips, randomized testing is the way they test it. And they have to do that basically, because the cost of fixing a bug once it's out and down on silicon is so high that you have to do everything you can to make sure that you have as few bugs as possible. And their randomized testing is just the default way to do it. You set up your environment and you spend a lot of time building a generator that will flood that circuit with data, and you will look for failures. And in the hardware industry, you actually see that they will say that as much as 70 or even 80% of all the engineering effort they have is on testing, because it's so important to get this right. And I think we're losing out something here in the regular software industry, if you want to call it that. I think this is a technique that should be much more widespread because it's really, really nice, and it reduces a lot of work, and it's fun, interesting to see when it works.
But it's not a lack of tools, it's a culture.
I think it is, yes.
In C#, for example, you have an implementation of QuickCheck, and if you use NUnit, you have the combinatorial
Yes. Yes, I think it is. I think you're right. But no. But I think at least for the type of testing I've done here, I think that type of features that are coming into C# now are features that will make it much easier to do this type of operations. And hopefully, I think there is a QuickCheck port for C# as well. I never use it myself, but it would be interesting to look into that. All right, so I'll just do a short summary of what I've talked about. So C# 7 introduces features that are suitable for this type of functional programming techniques that I've been mentioning here. And my hypothesis, and what I hope you also agree with now, is that these features are more than just syntactic sugar, because these new features enables us to write our code using different patterns. And that is one of the really big advantages of having something coming into a language, not just as a library or something. It's something that we can all agree on. This is part of the language. This is something you can use. And actually, when you think of it, every feature that is in a language is an encapsulation of some form of a design pattern. If you think of a very common thing such as inheritance and virtual functions, virtual methods, that is something we use all the time in an object-oriented world. But some point in the distant past, in the C world, someone was building that type of patterns using C, a non-object-oriented language. And it was not until C++ and these other object-oriented language came about that this was really mainstream and things you would do all the time. People will build virtual functions with all these virtual function tables and all of that in C. But having them as part of the language makes them so much more easy and reduce the threshold so much for actually leveraging that type of patterns. All right, and just like lambda expressions and LINQ provided the ability for us to do stream-oriented processing in C#, my hypothesis is that tuples and pattern matching will enable this type of coding style that you have seen during this presentation. All right. That's it, some references. This is the demo, link to the code I used for the demo here. So if anyone wants to look at that and play around with it, you can see it here. It contains some cheats for the demo, but just so you know. So don't be angry at me that I've been misleading you. But it's you can run it. This is the link for that QuickCheck talk that I mentioned earlier. And finally, this is a talk I did here at Foo Café a number of years ago, where I talk about, it's a similar talk where I talk about LINQ and lambda expressions and the concept of stream-based processing C#. All right, that's it. Thank you very much.